All right, welcome back. Let's talk about cycloaddition reactions, specifically the Diels-Alder reaction. Okay, so this is a very important reaction in chemistry. It's been known for quite a while now, and it's a very useful reaction for making rings in particular. As you can see here in this scheme, we have a diene, basically a conjugated molecule, which reacts with an alkene. Now, doesn't necessarily have to be a regular unconjugated alkene, but you do need a system that contains 4 electrons and 2 electrons. This will become more self-evident a little bit later in the explanations. But you're working with basically a conjugated system, at the very least, for one of them. And I'll highlight this some more later, but also notice that the alkene right here has some electron withdrawing groups, basically groups that have uh, relatively good electronegative elements that pull electron density away from the double bond. Um, that enhances this type of reaction. So I'll be highlighting that later. But notice that in this reaction, we end up not just reacting these two molecules with each other, but we end up forming a full-on cyclic structure. And additionally, notice that out of the 3 pi bonds, only one of them survives. Not exactly on the original spot, but there's one pi bond that remains in this molecule by the end of the reaction. On top of that, there's a lot of regiochemistry and stereochemistry that ends up being very specific in the molecule. And this is not me drawing random dash bonds and ball bonds. As you'll see momentarily, there is a very specific way in which this reaction happens. And based on the discussions that we've had so far in the previous videos, you may already have determined that it has to do with orbitals. All right, before we get to that though, we gotta, present to you the two fellas, the good fellas, Otto Diels, whose reaction, basically this reaction is named after, and of course Kurt Alder, who basically worked on this type of reactions around the same time. So they were both, acknowledged with this reaction. And between you and I think I don't know. Deals gives me a little bit of a Breaking Bad vibe to him, so maybe I lean a little bit more towards Mr. Otto. But out there, I guess he has the better picture. Let's be honest. Like Deals, I don't know where he was looking at. It almost looks like they just took a picture of him just walking down the, down the hallway. All right. Anyway, so just to match, molecules to faces, so to speak. All right, but the conjugated alkene, we refer to it as the diene, and that's probably pretty obvious by the fact that you have two alkene uh, conjugated alkenes present in the molecule, right? So diene. Now this one, on the other hand, has a pretty interesting name. Since we're reacting diene with the regular alkene, we don't just call this regular alkene because that would make things too easy. Instead, we call it a dienophile, as in the molecule that wants to react with the diene. And when we get to the cyclic structure, this is called the cycloaddition product or the Diels-Alder product, alternatively. Okay, so I've been making a big fuss about these orbitals, so now it's time to start bringing them into, the perspective. All right, so if you think about the diene, we're talking about 4 carbons that contain pi electrons. And what that means is that there's 4p orbitals in sequence. And because there's 4p orbitals, we have 4 molecular orbitals to account for, right? So we have the orbital on the bottom, which is fully in phase. The next orbital that is once out of phase, right here in the middle. Then we have the orbitals that are out of phase 2 times, once here on the left side, once again here on the right side. And then we have the final orbital that is fully out of phase as you go from left to right. Now, the easiest way to kind of go about this in terms of determining which orbital is the HOMO orbital, which one is the LUMO orbital, you simply count how many double bonds your molecule has that happen to be conjugated. And this molecule, the diene, has 2 conjugated pi bonds. So that means that you will have to use 2 molecular orbitals to fully account for the electrons present in those double bonds. So basically what I'm saying is that this second orbital is where we will have the last set of electrons present. So this is the highest occupied molecular orbital of the diene. At the same time, if we look at the dienophile, there's only one pi bond, so we only have the two p orbitals. We do have to have two molecular orbitals in total. But because this is only one double bond, the HOMO of the dienophile is the bottommost orbital. And what that also means is that the second orbital here, the one that's anti-bonding, is the LUMO of the dienophile. Now, technically speaking, as far as determining the outcome of the reaction, it makes no difference whether you look at the LUMO of the diene or the HOMO of the dienophile. But since the dienophile tends to be the molecule that bears the electron withdrawing groups most of the time when this reaction is successful, it makes more sense that the LUMO of the dienophile will be the one lowest in energy and the most attractive to electrons. So, just out of habit, you could say, we go with the HOMO of the diene and the LUMO of the dienophile. All right, so this is the key idea. I mentioned to you earlier that, yes, these two are the frontier orbitals, but here's where you have to really keep in mind. The HOMO orbital is the one where you have the highest energy electrons in a molecule. And the LUMO orbital is the one where you have the lowest energy vacant orbital where electrons can be added to. And if you think about it in those terms, well, the HOMO is nothing more than a nucleophile, whereas the LUMO is the electrophile. And electrons from the HOMO orbital of one molecule will be reacting or interacting with the LUMO orbital of the other molecule. So here's where the full analysis of what's going on with these things kicks in, because if you think about the regular shape of this thing, right, it's not a line, right, it's more like a little chair section, right, that envelops onto itself. You look at the HOMO orbital of the diene, right, and you have the shading on top for the first two carbons, shading on the bottom for the third and fourth carbons, right? And then you look at the LUMO orbital, where you have this anti-bonding section, that lines up perfectly with the ends of the diene molecule. Because notice here, the orbital down here on the left side is matching up in shading with the orbital to the left side of the dienophile. And then the orbital on the rightmost portion of the diene matches up with the lobe of the orbital of the right side of the dienophile. And so this is actually the attraction that brings these molecules together, the fact that they're forming a bonding interaction between the extremes of the two sides of the molecular orbitals. All right, so let's see exactly what that does for us. And I want to get a little bit more specific with the visuals so that you can see clearly what needs to happen right here. All right, so to make this more specific, right, we have the pi bonds depicted by the p orbitals going up and down. And what that means is that the groups that are present on your alkenes have to be going in and out. So notice that I drew the methyl group right here, going behind us, and then the hydrogen is also present up here is pointing towards our direction. At the same time, the ethyl group up here is pointing to the back, while the methyl group is pointing in our direction. So in essence, I've taken this molecule and I moved it 90 degrees in our direction, and I had it fall flat on its on its side. And then this one, this is basically a trans alkene. When you draw it in the same fashion, you have one cyano group pointing behind the board. You'll have the other cyano group pointing away from the board. All right. So for this to kind of work out, what needs to happen is that these lobes have to rotate until they end up fully interacting with the orbitals that you see here for the dienophile. And since the unshaded orbital on the left side and the shaded orbital on the right side of the dienophile kind of restrict what needs to happen, what this means is that the left side of the diene molecule has to rotate counterclockwise to bring the unshaded lobe closer to the dienophile. And then the right portion of the diene has to rotate clockwise to bring the shaded region closer to the dienophile as well. So basically, you will have opposite rotation happening on either side of the diene itself. We call this a disrotatory rotation. All right, but check this out. I should rotate those orbitals so that they come closer in contact with these pi electrons. And I move the dienophile 90 degrees, basically made it fall 90 degrees flat on its side so that you can kind of see now where the hydrogen and cyano need to be pointing by the end of the reaction. Now, what I want you to notice as well is that when we rotate this counterclockwise, what we're also doing is rotating the groups. The methyl that was on the back is now going to be pointing downwards, as you can see right here. And the hydrogen that was pointing in that direction, once you do the counterclockwise rotation, will end up pointing upwards, as you see right here. Likewise, the clockwise rotation will take the group that's on the back and it's going to have it pointing below, as you see right here, and then the methyl is going to be pointing upwards, right? So you have this kind of like axial and equatorial, type of bonding situation happening. All right, so once this takes place, you end up making the actual covalent bonds right here. And when you consider where everything ended up as a result of these rotations, this rotary rotation, what you should realize is that the hydrogen is above the methyl. And on the right side, the methyl is above the ethyl. At the same time, the cyano groups are opposite of each other or trans to each other. So on the one hand, here on the left side, it is on the equatorial position, or rather below the hydrogen. Here we have it also on the equatorial position, but it is above the other hydrogen, right? And that gives you that trans configuration. And then if you want to take this back to the original drawing we had, well, this is technically what I was depicting, that the methyl group with the dash bond is positioned below the hydrogen, that the ethyl group in the dash bond is also below the methyl group present on the same carbon. And then you have one cyano group that's pointing up or being positioned above the hydrogen, one cyano group that is below the hydrogen, which is exactly what we see in this molecule. So this way of looking at the molecule from the point of view of the orbitals is absolutely outstanding, because for the longest time, when this reaction, was investigated, people didn't quite understand what was going on with the regiochemistry. Why were they getting certain results, with certain alkenes, with certain dienes, dienophiles? And it wasn't until Diels and Alder both started looking at the orbitals and thinking about them that the explanation presented itself beautifully to them and then to the chemistry community alike. All right, so we're going to stop this video right here, and I'll continue talking about the opposite reaction, the retro Diels-Alder reaction. So I'll see you in the next video.